So we're going to be talking a lot about different, dequantized quantum algorithms, quantum-inspired machine learning algorithms, tensor networks. It's basically if you want to really find out what to focus on, this is a good technical talk for today. So this will be discussion 120. This is Thursday, February 1st, 2024 for quantum algorithm time complexity analysis and future QML/QiML. My name is Kevin Kawchak. I'm the founder CEO of Chemical Q Device. So what we see here are actually a bunch of the quantum algorithms that have been dequantized. I believe they tend to be smaller ones. And so you see anything from, matrix inversion, quantum singular value transformation, these types of things. Now, that's the first part is covering dequantized our algorithm up at the top here. And so basically, there's time complexities are similar to quantum algorithms, meaning that they're basically they can be polynomially slower than the quantum algorithm. And it's basically saying that the quantum algorithm, if it were to be some time to use it on a quantum computer, would not have exponential speed up. That's the main thing. And, it's good for quantum inspired machine learning because we can use these. So some of the dequantized algorithms, are more difficult to use, or they use a different approach than, say, a classical, machine learning algorithm would. And so the next section is the tensor networks, and I've always wanted to study this in more depth. And so the three mains are matrix products, state, tree tensor networks, and then PEPs is the last ones. And they all have their kind of quirks, as far as using them. And lastly will be the quantum variation algorithm simulation. This is what you most finally, find on Qiskit, PennyLane, and basically some of the limitations with running high qubits with that and trying to use data compression or optimize circuit partitioning and large scale batching, or some of these approaches to, run. These are state vector algorithms, so they give exact solutions, unlike the approximate methods with tensor networks. So it's good to explore running different parallel architectures. I was able to do this with 20% better loss efficiency over running a single circuit at low to moderate epochs. So the first thing here is there's a lot of different directions behind all of this. And the reason why I keep referring back to this paper is this Hoyne et al. Paper from later last year, is because it kind of puts it all together as far as we are using GPUs and CPUs, okay? And then so what are all the different ways of using, classical processing for these algorithms? So these are the dequantized algorithms so far, and I'll get to another author that kind of was behind a lot of that work. The tensor networks that I'll be talking about, some of those quantum variational algorithms, and they go on to other methods. It's a big paper. It's over 50 pages, and it's very dense, and it contains a lot of technical information that's useful. So Tang et al., or actually this is Tang's, this is her dissertation. So before they were trying to get speed ups and these types of things, but were actually able to dequantize a lot of the algorithms. So this is what they believed before, as far as being best candidates for exponential quantum speedups. So the bluer is the worst, towards yellow is best. So we see topological data, Gaussian process regression, recommendation systems that they had, or she had, at the top of the list. And there's others that do, these similar types of dequantizing algorithms thing. And this is after the dissertation work. So after, finding out that you could dequantize algorithms, very famous algorithms like HHL, these types of things, that everything on the right, you'll see support vector machines, very common, support clustering. So these are the things that we can use in QiML now in a dequantized version. But I think the main approach is basically saying, on a perfect quantum computer, if you were to run that algorithm, would it have exponential advantage versus a truly classical version? So for these on the right, it's no. And then for these on the left, you see topological data analysis and Gaussian processes. The author still believes that this can have, a greater chance of having exponential quantum speed up, and still using it with classical computers too. So here's these tables, and you'll see these types of things. And from what I gleaned from all of this is basically, at most small polynomial factors. You have to be close with the classical algorithm to the quantum algorithm. So you'll see these for QSBTs, recommendation systems. And this chart is similar to the Hoyne et al. Paper from later last year in 2023. And this is the Hoyne et al. Paper, their version of the story. So it's very similar to what was shown with Tang's dissertation. Okay, so matrix product, states, or any quantum state can be exactly represented by the MPS. Now, it's an approximation. The whole technique is, but it's if you were to line up a circuit with the nodes of a tensor network, that's something that you can do, or has been done before. So it can handle certain tasks that deep learning can't, such as dimensionality reduction and representing high dimensional data. And it's basically how these nodes are connected. So if you look at like a traditional transformer or convolutional neural network, as it goes layer by layer down, this has a different objective. This is mostly if you have a single large quantum circuit, and then you want to be able to run it on classical hardware for many years to come. That's how they're going to be run. And they've had a number of experiments with it, and I'll show you some charts after this that show that it's still a developing process, because you're losing some of that exact representation of a state vector algorithm that we use all day. But the hopes is that we can go up and I think NVIDIA has scaled this to thousands, and another person from NVIDIA says 10,000s of qubits, with tensor networks. And this is just to give you an idea of what they look like. So this is the one dimensional, so it's pretty straightforward. And, so basically this is the most computationally friendly of the other two that I'm going to show you. However, with the other ones, you can do more with it. So the enter tree tensor networks, and you'll hear of Maras, with these types of things. So in all these, they're reducing the complexity of a single, large tensor or quantum circuit into smaller tensors of smaller rank, instead of attempting to simulate a many qubit circuit limited by RAM. So if you do not know, when you go to, create huge circuits and run them on classical computer and hardware, the issue that you run in right away is RAM. You get exponential RAM, even as low as like 16 qubits. But, to do quantum machine learning, 30, maybe a little bit more, because there's the data set and that type of stuff too. So they say it's less general than PEPS or MPS, right? So it's a tree where the structure aligns with the physical system. So you start to hear, many body systems, these types of things associated with, these tensor networks. And, the other one to keep an eye on, I didn't include the structure, but the Mara is kind of like a hybrid of like, it basically looks like an MPS with a tree tensor network, with the MPS kind of like mixed in with the trees, is what you'll see. And then, so this is a 2D version. So you see like this can be an issue on classical hardware. And, for two things, with RAM, and then losing your accuracy, or your loss, those types of things. So, it's a heavily studied field. And that's what I keep seeing, is that, it has to improve more. And I've had better luck, I would think, with parallel architectures than some of the other papers that I've read with tensor networks with classification. It's parallel is a little bit more straightforward. So here's the other one, is PEPS. So you can see PEPS is going to have this 2D grid-like nature to it. And, so there's certain advantages. So they say the PEPS decomposition, polynomial correlation decay between network parts, and then the MPS is exponential decay. So that's an advantage for PEPS in this specific case. So it really just depends, it depends on your data set. It depends on, how much RAM you have, these types of things too. So the other thing, grid structure, and Yeah, so exact calculations for PEPs are practically infeasible for larger systems. So you get into like these, things that easily become the main issues that you have with dimensions and these types of things. So this is what PEPs looks like. It's very similar to MPS. So those are those three. So on the left, you'll see, so an MNIST data set is very straightforward. It's 10 classes of digits. And a fashion MNIST is a little bit more challenging. It's got, clothing. It's 10 digits as well. It's a drop-in replacement data set for MNIST typically. And you'll see that the classical, a convolutional neural network is still doing better, on that set. And I read and I actually presented earlier on a BMW tensor network paper with Max Planck Institute. And they said the same as like, they just, I don't know, you get, all sounds encouraging. And at the end of the paper, it's just, it didn't work for them as far as getting the type of performance that they were looking for. It's an efficient method to, especially if you want to start off with multi-qubits and then now, split it into smaller tensors, stuff like that. So in the upper left-hand corner is where we're at. So dequantized algorithm, all these have quantum nature at one point. So dequantized algorithms originally started with some quantum algorithm or quantum-inspired machine learning algorithm, and now they're dequantized. So there's no quantum mechanical information. They're more similar to like a classical algorithm, but their roots are based in quantum mechanics. So you see tensor networks. If you were to look at this as a scale of like the percent of quantum mechanical, qubits with rotations, tensor networks are a little bit more architecture, whereas the VQC and quantum kernels is, for the amount of processing that you're doing is going to have a higher density of quantum processing in it. And you'll see in this bottom right one is they basically said that for binarized MNIST, which is an easy task, typically, 2 classes out of 10 digits, is that, the MPS is doing better than some of these other approaches, with the classical actually doing, fairly worse than the other methods here, classicals by the star. And then, so basically, in the big scheme of things, will dequantized algorithms will do it for tensor networks and quantum variational algorithms and other things too. And I think it's more of the very basic, like an HHL, these specific algorithms that are smaller. And it's more towards those like techniques that are constantly happening, like matrix inversion, those types of things. But nonetheless, it's something to keep in the back of your mind, because like I said, there is a contingency of people that want to see, hence if a quantum computer ever comes around, will there be an exponential speed up algorithm left, because that's the process that had to be completed. So anyways, you can run dequantized algorithms, tensor networks, QVAs on quantum inspired, and according to other people saying an immediate financial impact, and we're strictly using GPUs for quantum algorithms. So this is kind of the landscape. And like I said, if you haven't read this paper, this is like my 3rd or 4th time going back into it, like deep diving into it. It has a lot, especially if you want to see exactly, speed ups, those types of things too, is there's a lot of information there. So this is QVAs. So basically QVAs, and tensor networks too, and, dequantized algorithms, you're going to use a classical optimizer in this process. And it's the same thing as anything with machine learning, except now you have quantum mechanical information, and then the parameters are the rotations on the simulated qubits, okay? So the circuits consist of embedding, variational layer, trainable quantum parameters and measurements, and that's the typical gate model. You can also do simulated annealing, which is gateless as well. They can be viewed as quantum analogs. So like when I do parallel quantum circuits, is that, it's inside if you have two quantum circuits in parallel, it's inside like a torch neural network, but the circuits themselves can become quite complex in a different way of processing data than conventional methods. So the upside with this is basically you're getting the exact expectation values. So if you have a demo or a notebook, or if you've created one too, as long as the notebook is deterministic, meaning that every time you run it, you get the same exact accuracy and loss, for every single epoch, then it's a good ground to start, building algorithms, benchmarking devices, these types of things. It's a good place to start. And the software behind this circuit cutting, mid-circuit measurement, a lot of this is for QiML and for QML, qubit reuse, tensor networks, and then these parallel neural networks that I'll talk about here too, is it's one aspect of basically saying like classical hardware works so good, it's advancing at a much higher rate as other quantum technologies. Let's just find a way to make this work because we want to run huge circuits, right? So that's what a lot of these approaches are. And Xanadu or Penny Lane, they took I think it was 129 qubit COA algorithm and did some circuit cutting, and was able to do certain tasks. And like I said, with NVIDIA, they've scaled up the being able to simulate tens of thousands of qubits, but I don't think that's for machine learning quite yet. So we see this too. So classical hardware will improve with bandwidth and storage. We know what's coming out. It's a working technology. So Q2 of this year, 1.4 times the bandwidth, 76% RAM, more RAM. So that's taking it from 80 gigs, like an A100 or an H100, and then up to 141. And then parallel architectures, and I've had a lot of success with this, is basically, if you look at it like, if you want to run something, what do you want to do more? Do you want to do more machine learning epochs on a single circuit, or do you want more of the algorithm up front at lower to moderate epochs? And that's what I found is basically the more, you only need one parallel algorithm, so two in parallel, and 3, 4, 5 work as well. But as far as loss efficiency, it's just fine just to do two in parallel for that specific case. And moving forward with this is that I was able to run a single qubit too, which is typically hard to get good results. And people just say we need more qubits, for other models. And I figured out a way to basically get effective numbers of parallel qubits between, running a single circuit at, 320 in parallel versus like 10 qubit circuit at 32. And so that's basically is using single rotational gates. And I've seen other parallel algorithm work, especially in the beginning of all this before the QML stuff came in, is they're using parallel architectures to get better performance. It's worth to check out. Now, I asked a question, a day ago on LinkedIn, is which application will have the lowest time complexity? And there's many demos out there, and we're kind of like, barraged by all of this. And I can understand those that are attending, you just might not have a complete grasp of what's going on as far as, should I run this convolutional neural network demo that Penny Lane has? And, I believe Qiskit has a similar one too. So, you really have to read the literature, right? So many places won't just tell you out front. I had to learn all this through literature, on top of Penny Lane offering a very good platform for it, and Qiskit having some demos too, and Cirq having some stuff too, and TensorFlow Quantum and PyTorch Quantum, those types of things. But it was in the literature that I found these things that just kind of like blaze it out flat. And anytime that you're looking to get into something, so for instance, this Penny Lane demo is non-deterministic. So every time you run it, using this approach of a pixel goes into a qubit, you're always getting a different answer, similar answers, but different every time you run it. So that's one of the things to look forward to. So this is one approach to it, and you see the quantum circuit here. Now, I've talked about the quantum transfer learning demo ad nauseum from Penny Lane. Now, here's a different case. So they're training off the source task, this data, and then these parameters that they figure out from this circuit are getting transferred as the starting spot, for your new data. And transfer learning is a well accepted and encouraged, and even for vision transformers or anything else. So a lot of this is borrowing for those concepts. So, which will have the greatest impact, as we think about time complexities and efficiencies and these types of things, is like, I don't get that right away as far as like on the platforms, Qiskit and Penny Lane, as far as like, well, I ran each of these twice, right? And I modified these, but was that the correct approach, or should I have changed something else? So here's a Qiskit example. And auto encoders or quantum auto encoders are thought to be, pretty promising. So this is, if you're just coming over from classical, this is an example of a circuit. So what we have is we have a single classical qubit or a single classical bit, and then this auxiliary bit. So 1, 2, 3, 4, 5, 6, 7. So we got 8 qubits, one auxiliary bit that does the measurement later, and then all of this, the encoder and these types of things too. So I think where the industry is heading, I don't think it's the most productive thing to focus most of the resources on quantum computers. I think that we have enough with dequantized algorithms. We have QiML algorithms, tensor networks, because a lot of people are sold on tensor networks because of the high qubits, right? And I think it'll come as getting the performance, but it's not a direct, it's not an exact solution that you get. And this is a Penny Lane quantum GAN. So this is the generator. So this quantum circuit represents the generator off of the generative adversarial network, is what this one does. And I think Penny Lane has 2 demos like this, and Qiskit has 1. And it's just, you have to keep an eye out for if it just takes too long to run. Unless you can run a quantum circuit and it's unique to that specific application, no way else can you run it classically. The other big thing is going to be time, right? Time to get to that perfect solution. So I took a couple, MIT algorithm courses, this week, and that's what they say. It's, efficiency, time, the exact solution, and the ability to communicate your results, algorithmically to other researchers too. And then this one I spent a lot of time on. And like I said, I found that the most efficient setup for their Make-Moons data set was to use 2 circuits in parallel. So I calculated it based off of a loss efficiency, meaning that for a specific time, I get 20% lower loss having 2 parallel algorithms than a single one. So this one can go many different ways. And in fact, once tensor networks are somewhat similar to neural networks, but their objectives are a little bit different. And, I would say the main one is just to be able to run a huge quantum circuit. And then on this specific one, you could do series. I tried series. It didn't work out, meaning, one quantum circuit after another. And like I said, like I could go 3, 4, or 5, and I did, a significant amount of research into this, and those also had an advantage over running a single circuit. But the double one, seems to work the best. So when you're thinking about these things, do you want more algorithm? Like, do you want that's essentially what a parallel circuit is, or do you want more machine learning? So over the course of time, like if I get up to 150 to 200 epochs, the machine learning takes over as opposed to the having the parallel circuits. So, it's like processing benefits and when you want to get them. And then this last one, I was actually able to take this one. This is Fourier series, but these papers get quite in depth, and it's good that we've gone through several iterations of these, and you'll see the Qiskit researchers, but more so Xanadu researchers, which is Penny Lane, putting these things up. And it's all fine in paper, but I just ran a simple embedding with the variational circuit and was able to beat these accuracies. So it just depends. And, there's some theory behind a lot of this. Now, this is kind of a cookbook. So these are guidelines, and I'll just read over a couple of these. So basically, most quantum linear algebra tasks over low dimensional data can likely be dequantized into a classical variant, provided SQ access is available to that data. So the 2 main things are typically QRAM and SQ access for that specific thing. And So say, for instance, several high dimensional problems have not been successfully dequantized despite SQ access. So this is more of an issue because I believe, because this is how the paper is set up too, is dequantized algorithms are fair game. They were originated with some quantum algorithm and we can use them. But on hardware, it's an issue because if they're claiming that they can use it exponentially and it's been dequantized, then that's an issue. So here's another one. Dequantized algorithm matrices must be of low stable rank, have a small condition number, or be relatively sparse and may not be compatible with real world data sets. So you have to get this from all directions. So the Tang, Ewan Tang's dissertation, and then the survey that I've been citing here, they all kind of shine light on it from a different direction. And you as a researcher, you have to know that these things exist, these three main categories that I'm going over here. So other researchers, Chia et al., some other restrictions there too. And the other thing is this is mentioned a lot, is the exponential speed up achieved by the quantum algorithm. We're relying on specific input assumptions about the user product preference matrix. So meaning the way it's set up, and that's typically what they go after is the exponential speed up algorithms, right? Because that in potential in many years from now, if a quantum computer became a lot less noisy, that would be something that you would run that task, even though it probably can't run it on a in a machine learning way, more on like an auxiliary way. Okay, so the end of this is basically this, is try to experiment with algorithms conceived from quantum mechanics. You would try dequantized algorithms, okay? It's an up and coming field. If variational quantum algorithm performance is poor, use parallel quantum algorithms because you don't need more dimensions, these types of things. And to approximate high qubit quantum states, use tensor networks. So obviously the issue, besides that binary classification one with the MNIST data set, are typically a little bit, it's harder to get your correct solution using tensor networks because they have to make certain assumptions to get to fit, to break tensors into pieces. So here's basically, so these are a lot of the quantum machine learning articles here, and it's derived from the Huan et al. And I made this table. And a lot of it, so Vidic was a founder in this, and you'll see some of these other people here too. Cerezo, he's at Los Alamos National Laboratory, leading up to today. So, this field is still projected, to do very well with compound annual growth rate. And I've heard, billions of dollars by the end of this decade. And then you have the support of the industry, especially with Sandbox AQ, with tensor networks, saying that they're going to use that with GPUs. And NVIDIA on its own, scaling up experiments with tensor networks and, GPUs. So the future's pretty bright. And here you see, so this was, 2023 was not done. But when they did this survey, they found that the quantum inspired in machine learning keeps going up. Combinatorial optimization is more like the first generation of quantum inspired algorithms that did not do machine learning. Okay, so those are kind of they became abundant at one point. And at this point, obviously we're more interested in trainable models. So it doesn't include the combinatorial ones. So if you're just brand new to this, so this is basically what we're talking about. You get classical data, goes into a PQC circuit, and then you have to, measure it. So this is back into bits on that specific one. And then again, so if you haven't seen this before, so you see, on a specific qubit, a circuit which you make, which has the algorithm in it, it's rotating the simulated qubit in a specific manner with these. And here's a bunch of these benchmarks. So I haven't had a chance to go through these as far as running them, but I think these are some of the ones that they'll say like Gruwenk or, trigonometric to, try to prove some time complexity with that. Are there any questions at this point? Any specific slide? I saw, some people definitely come on.
Yeah, I have a question.
Yeah, go ahead.
So what I'm gleaming from this presentation is that quantum machine learning has very specific use cases because it's a very computationally demanding sort of process. So, in your opinion, what use cases specifically for QML, and why should we use QML and not a dequantized algorithm if it was still able to sort of get the same or better results?
Well, you could still do machine learning with dequantized algorithms. So that's the key of like a dequantized support vector machine. And as far as what's primed, now I personally I've run all the Penny Lane and Qiskit demos twice for machine learning, and I found parallel quantum algorithms to have the best increase as far as you can't go any higher on dimensions like you can with tensor networks. So, in weighing all these things, if you want to do stuff now, it's going to be harder from all these papers, to do dequantized algorithms because they have their own uh, nuances. You're taking a quantum algorithm, you're turning it classically, and the speed up is there, but there may be other issues in running it. And if the only thing you want to do is run huge circuits, you can run tensor networks today. And NVIDIA has Q Tensor Net. They have Q State Vec, which is for state vectors too. So all of these things are available. The issue that you get is the RAM. So if I ran, even parallel quantum circuits on that demo at 20 qubits, that's over typically over my 51 gigs of RAM on my CPU. The other issue going on is PyTorch and TensorFlow is not fully compatible with GPU use with Penny Lane or Qiskit. So to run at accelerated rates, you're going to have to use like on Penny like Penny Lane and NumPy as opposed to PyTorch or TensorFlow. So yeah, you just have to be aware of all these things because if your end goal, you have to be aware of things that could not help you reach your end goal.
Yeah, so specifically, I think the main comment I have on quantum machine learning specifically is the quantum part helps us process more data exponentially, but the cost of the RAM is the main issue when you're trying to sort of go with this. And when I was also trying to train my own models, also even the technical implementation was exceptionally hard because aside from the machine learning itself, you also have to know how to integrate circuits. Yeah.
Yeah, these are issues. So RAM, if you're using, so you always want a time complexity like those formulas that they come up with are like basically the very fundamental part. If that's not right, then it's pretty much guaranteed nothing else will. Now, if you run a bunch of demos and you can compute a loss based on a time, or I'm sorry, you could compute a loss efficiency based on loss and time, like a 1 over loss times time, and compare that versus traditional algorithms, that's an effective approach. And I think there was actually a slide here. It says if state preparation cannot be done in polylogarithmic time, then exponential speedup cannot be realized. So there's quadratic speedups, which I think people are still saying, with these quantum algorithms that we have, like a 2 to the n. But basically, if the embedding is taking up, if it cannot be done in polylogarithmic time, then you don't get the exponential speed up. So you have to be aware of that because I think embedding takes up a lot of it. Just getting the classical data in, and there's some associated costs with measurement too. But yeah, I think that just with all the literature I read, you have to stitch it together, right? It's really, with this specific paper and the Tang paper or dissertation and these types of things, is it part depends on your problem, how much data you're bringing in. And they say for certain things, to not even, okay, here's another one, state preparation assumptions should be matched with L2 norm sampling assumptions in the classical model. And it's tricky, right? Like how in these, demos or you create your own, you want to hot swap a quantum algorithm for a classical algorithm and compare that directly, right? That's a
Mm.
goal. And I think that these things are achievable, right, to do on the programming side of things.
Yeah, so just the last comment. I think the thing I'm trying to think to myself is, so there's a cost and then there's a benefit. The cost obviously is you have to have the expertise in machine learning, some software engineering and quantum to be able to implement the algorithm. Then of course, as it continues and continues, the RAM exponentially increases. So the question I'm trying to ask myself is, what specific case scenarios would we accept that cost for high dimensional data? Let's say if we have like a data set that if we try to run through like a classical algorithm, it wouldn't be able to process the data efficiently in good time complexity.
Well, the number one thing is qubits, right? So qubits is what will get you on RAM, and depth less so. And when I did these studies with the parallel algorithms, you know, even if adding an additional parallel algorithm to it, it was increasing, RAM and runtime linearly. But as the circuit got bigger, like 10 qubits compared to one, that slope increases.
Mm.
So the main thing is qubits and RAM, and there are certain types of gates that I don't think have been proven to work very well, like for classifications, like entangling gates that take a lot of cost. And part of it just depends on the algorithm too. Like tensor networks, I can't always do highly entangled networks. So if you want to go huge with a circuit, that has to be one of the factors. I think it's like lowly entangled is technically the case with that. So it part depends on your data. It part depends, on the model. There's a number of factors to consider, but I think the big one, cost, computational cost, is the qubits. And, you know, can you run parallel algorithms? Can you just run the thing longer? More epochs, more time.
Yeah, okay. Thanks.
Yeah, you're welcome. Anybody else? So I think that this is a good, this paper that was created, and other of my colleagues have referenced it too, is definitely a good place to start, because even if you want to, because now with the algorithm issues, with non-exponential algorithms for quantum hardware, and then you have latency, noise, cost, availability, these things are just piling up as not being user friendly for quantum machine learning. Like when I think of machine learning, I think running experiments late into the night and running experiments overnight and not having issues connecting to or with the number of GPUs available or CPUs or those types of things. So again, I think the hard will have its day, but it'll be more for like a specific task, like everybody else has said, like it's for a big problem, fixing some classical algorithm that's used in machine learning or quantum machine learning, these types of things. So it's really hard, it's really important to, basically, know all this stuff, but know when to implement it, like a dequantized versus QiML algorithm versus, VQC, the parallel quantum algorithm. But the biggest issue known is the RAM issue with qubits. And that's, why there's circuit cutting, there's, parallel algorithms, there's, tensor networks, mid-circuit measurement, qubit reuse, these types of things are to help that process. And like I said, the industry is as far back as November, I think it was 13th, classic Sandbox AQ, actually, I think earlier, maybe a couple months before, NVIDIA, it's basically used for most of this, is, Terra Quantum AG and even Google Bard, using QML to help the process, to even help quantum computers. I've seen it for Google Bard. So, but I think you're going to see all of this. You're going to see this dynamic landscape between hardware and CPUs, GPUs. But I feel like the bulk of this is going to be on GPUs, at least for the next several years, just because it works. It's a working technology. And then with all these software and better GPUs, the H200, that, this will help that process too.
Just another comment, specifically when it comes to training a model, what are your main tips in terms of actually like evaluating it on the machine learning side? Because I know like there's training loss, the epochs. So what are your like general tips if you're trying to like train a data set on a deep quantum neural network?
And you're saying with GPUs?
Yeah, with GPUs, assuming that you have the GPUs.
Yeah, I mean, as far as Penny Lane and what they have, they kind of heavily rely on Torch. Number two is TensorFlow, and number three, as far as like the cool stuff with the GPUs, is NumPy. So if you want to do that on Penny Lane, you're probably going to have to use NumPy. And the other tricks for it, as far as getting good performance and this is working kind of thing, is everything goes into they're quantum inspired. So everything is classical data processing, classical data generating. And it's quantum inspired, meaning that these algorithms are influenced, meaning that they're similar in quantum nature as if we're trying to get it, the hardware to work. So that's the big thing is that, but they don't have the issues. They're, they return the right answer right away as opposed to running it on hardware. And they can be copied. So there's a no cloning theorem, that kind of stuff. There's just all these issues over there. But it's been done, so I would look, if you're looking for that awesome use case, GPUs, Penny Lane. I shared this, I think 2 weeks ago. It's the QAOA, quantum approximate optimization algorithm,
Yeah.
with tensor networks, GPUs, and the notebooks on GitHub with that specific one with the algorithm.
Mhm.
And I've done benchmarkings on the graph embedding problem, but just fixing the model and just switching out the GPU versus some other CPU.
Yeah, so I'm a user who, of course, interacts with technology a lot. Can you like suggest a book or like resources where we can sort of continue reading on this?
Yeah, well, I would definitely start running. Running is going to be the key factor. If you can't get to the point where you're running experiments throughout the week, it's going to be tough. Because you learn from that. I was trying to fix two Qiskit demos, and basically I want to get 100% and zero loss. And one is like a continuously training, those types of things. But as far as resources, the demos are good. QHack is coming up. Here's a plug, although I'm not associated with QHack or Penny Lane or Xanadu. I think it's in a couple weeks. I want to say either next week or the week after that. What it is it's nonstop lectures of people leading, in academia pretty much, or industry a little bit. And, they're just sharing results and sometimes they'll ask them questions or interview them. And sometimes they'll have like these little meme contests, that type of stuff. But I think last year it keeps getting bigger. Typically it's in Toronto, but they do it, virtually because people can chime in all over the US or all over the world, is that, 30 plus demonstrations of their current research, that stuff, because you have to get it in the back of your head to learn it. And I'm not sure what your background is. So I would do that. Literature, if it makes sense to you. And the demos just teach you as you run them too. So I think that's kind of where I start is running.
Okay, so my background is in mostly computer science. Generally speaking, I'm more interested in quantum for its really granular, practical sort of things. The theory mostly I've done on myself, but I'm trying to get more sort of details on more like applied quantum technologies. Generally speaking, I work on the computer science and like software side. So, and I have done some machine learning, but mostly computer science.
Yeah.
Uh, I also signed up for that hackathon too.
Yeah, I mean one time a year thing is the Q hack thing. So I definitely wouldn't miss that. MIT has IQ hack, which is IQU, then hack. And these are kind of running at similar times, I think, as far as in the year. But that can help get you exposed to, they probably have very basic stuff too, if that's what you want. So yeah, it's the kind of thing that I believe in the Feynman approach, which is basically if I teach it really fast and I learn it, then I can develop what I need to on my own. So I use that, this platform to teach too.
Yeah, so what are your thoughts on a quantum machine learning and a classical approach, like combining those two to sort of refine each other?
Yeah. Well, you can already, so just to kind of boil all this down, you can run quantum inspired machine learning algorithms or QVAs or very small tensor networks on a laptop with other classical algorithms, if that helps put things into perspective.
Mhm.
And there's other, basically thoughts of any quantum hardware is going to need to use a CPU. It just has to. It just can't even work without a classical computer. But yeah, there's approaches where they'll have, say, for instance, you'll have quantum computer in the cloud, and then your classical computer on some other or algorithm on some other server. So this stuff happens all the time. It's just that there's so much noise, and for the ones that work kind of okay, there's cost and availability issues. So if you're working on a project, can you get it on, can you stay on it for a couple hours, that type of stuff, unless you pay. But yeah, I think the quickest way in all this, no matter what happens, say if hardware develops quickly or there's a breakthrough, that type of stuff, is you have to be running stuff that works, and you have to be able to compare your results in a non-stochastic way. So when you're talking about minute changes and loss and accuracies, all these experiments aren't going to work on hardware. You can only run them classically. So yes, you can run quantum algorithms, classical algorithms, all on the same laptop. The reason why we call them simulators or devices is because it's a separate part of a server or something that has dedicated RAM, like 50 gigs or whatever. That's what you'll run into, is you need a quantum simulator, and but all of these operations can be done on a single laptop at a small scale.
Mm. Um, do you know any specific papers that also point out for space complexity, or is it just time complexity?
Um, there's a penny lane time anomaly, so I don't know if that covers space, but I would really go to it's the penny lane quantum machine learning demos, because like I said, I've run 26 of them like twice. So as far as space complexity, I'm not too sure on.
Okay. Just one more comment. I do have my own sort of application that I am developing for like my own optimization library and like my own sort of new class of quantum computers, but I wanted to dig in more into quantum machine learning. Specifically, I wanted to also know in your business, what exactly is your application for quantum machine learning?
So far it's been medical images. I took so this demo had two classes. I took it to 4 to 10 to 44 class, and then studying that ad nauseum. And then I've also done a number of like FDA studies, NIH studies. Their current AI approaches are like there's so many FDA approved AI ML algorithms, and say, oh, which of these would have the biggest correlation to the quantum machine learning algorithms? Like, what's the easiest approach with that? So a bunch of that work.
Um, So what about genetic analysis? Because I know the LSTM model is used very extensively on that one. What about a quantized version of that?
Are you referring to genetic algorithms?
No, like so LSTM. So
Uh,
let me track back. So I was trying to train a model to analyze genetic data, and I
uh,
use an LSTM model to sort of train train it on the genetic data, but I wanted to know if you can quantize that for to train to understand genetics.
You can. So there's a gentleman, he's been on this discussion before. His name's Brent Raw, and he's used BERT models. So this kind of transformer with text. I think with DNA, I think that's been his thing. So I know on GitHub there's other kind of genomics with this is a Penny Lane demo, the quantum transfer learning, where they use that type of stuff. So yeah, there's a lot out there. And to any researcher that, if you want to, basically further all of this, I think that you have to get to the point where you're like, okay, well, I want to run it bigger now, but I don't have the software techniques or I'm limited on hardware. So I'm going to do the best that I can on classical with, on CPUs, GPUs. As GPUs get bigger and as their software gets better too. But like I said, like you have to have something that kind of works in order to build off of it. And if, say, I get approached by other hardware companies, I'm not really interested because I can't really run today. And I don't think I can learn an extreme amount of information, especially because I'm trying to do quantum machine learning, right? And not some, big quantum problem, right? So that's like a separate thing. But yeah, was there anybody else that had questions? And yes, and the limiting factor that I've seen, I mean, I see other people growing in the technology, but they're still kind of reporting other people's work. And, I probably have the leading medical QML repository out there, and it just takes time. Like you have to run benchmarks, and I've done like 4 or 5 algorithm prototypings, these types of things, building up to quantum, QTL models, those types of things too. Go ahead, Kashani.
Yeah. Hi. So I have a quick question. I was wondering to know, like, in quantum computing, there is a lot of complex numbers, and I have been working on some applications where the input data is complex, and when you just feed it right into the deep learning models that are currently used, you need to just do something about it. Usually divide that to imaginary and real numbers. So do you think that quantum machine learning would be able to help with that, especially like in medical applications? There are complex numbers. Like I know that in ECG or I think MRI, there are complex numbers that you need to process. And I think the biggest challenge in the normal deep learning is optimizing the complex numbers. And do you think that quantum machine learning could help in that area too?
Well, as far as I'm aware of, there's no real quantum data in it. You're not talking about quantum data, correct?
No, yes.
Okay. Yeah, so if it has complex numbers and you're saying you're not losing any information going into, classical machine learning?
No, I mean, I'm saying that I mean, I'm not really expert in the quantum area. I'm a computer engineer. So during my exploration phase, I realized that if you want to indicate quantum state, you use complex numbers.
Yeah.
So I thought maybe if you represent data as qubits, that they have complex states, would you be able to use that to
Yeah. I just don't know how much you're going to gain from it because, we convert images into, classical images into quantum all day. So if you're saying like classical complex numbers into quantum, is there an advantage over if they were just regular integers or floats, that type of stuff?
Well, I mean, no, my question is let's say your original data, your input data is complex.
Yeah.
Right now, you need to convert that to integers or real numbers before you can feed it to the model.
Uh-huh.
Which, intuitively, you think that this might not be like the thing that you want to do because you're separating the information.
Yeah. Well, I'm not quite sure. And then my other question is basically, I don't know how much you would gain, just using quantum circuits instead of doing it classical learning, because I don't know the cost of going from complex to your approach.
Uh-huh.
Because typically, we're more concerned about if it's already in quantum data, then we don't have to embed it. And then it goes straight into the variational circuit and that saves embedding.
Right.
And I haven't heard that before, but it's, probably worth researching.
Okay. Okay. Yeah. I mean, I was mainly looking to get to know more about quantum machine learning because it sounded like in order to be able to optimize quantum data, you might need to deal with complex numbers and be able to optimize complex functions. But I
Yeah, I
don't know
think the
much
best
about that.
thing that you could give me is there an algorithm? What is the algorithm that you're using now that converts complex numbers into the format that you need to use?
Well, I mean, most of the works, they have just took the real value of the input. Let's say you have a array of 10 complex numbers. You take the real values, you get an array of 10 real values, and then you take the imaginary, and then in total you get an array of 20, length 20, and then you feed that input, the array of 20 to the machine learning.
But you're trying to save cost, right? Computational costs.
No, I'm trying to say like intuitively, this seems like you are distorting the input data. You're changing the input data.
Oh, maintain fidelity kind of thing. Yeah,
Right.
that's kind of what I was getting at as far as like, if you maintain all of the original information, those types of things. Yeah, like I said, this is a really good question. I just don't know exactly. And, this is, it could be a thing. I just don't know how much you'll benefit, by going a traditional, quantum inspired approach of,
Yeah.
but it's worth it, right? Because just like, in all these algorithms, if you have a quantum algorithm that has a new utility that's not available traditionally, that's a key. And what you're saying is you're keeping fidelity if you processed it quantum mechanically, because you're just going more complex into complex.
Right. Right. Yes.
Yeah, like I said,
That's something that I'm really interested to know. But I think I need to do more study on quantum machine learning as well as like other techniques to be able to figure that out. But the reason that I asked this question was that because I know that there are really numerous applications in healthcare that they have to deal with complex numbers. I mean, beside just normal pictures, I think MRI does that, and also ECG. So,
yeah, I mean, the closest analogy I have for it is the quantum convolutional neural network. They call it the convolutional. So you have a block of your CNN with 4 pixels, and those pixels are imaginary numbers, complex numbers that get encoded into the embedding layer of the quantum circuit.
right.
So, yeah, I mean, this type of thing, I believe other people would think of, right? So if you're in industry and you have this issue, I don't think it's a unique problem. It's just one of those that I haven't been presented with before.
Got it. Okay. Well, but well, thanks for letting me know about that quantum convolutional network. I'll dig into that.
Yeah, I'll have the deck up. So the one that I'm looking at that might give insight, and
Okay.
Penny Lane has a demo on this. It'll be slide 17, and from there you could also search for the Penny Lane. They call it convolutional demo, which is a popular technique for image processing with quantum circuits.
We got it.
Any other questions? Anybody we haven't heard from? And it's the type of journey I think is unique for everybody, but I place an emphasis on running experiments. You're going to have to do some research at some point, like with this probably saved you time. It helps me tremendously. but it also helps, the people around me. But to run my next demos of, if I just want to run things to get 100% accuracy, zero loss, and all these, existing demos, that's one of the things I can do. But is there something else kind of opening up? Like, we want to use tensor networks for this, but we haven't thought of doing it this way. And, can you run some other variant, or other parallel architecture in an efficient way that gives the correct solution? Awesome. Any other comments regarding the discussion? I appreciate everybody coming on, and I want to emphasize, because I watched some of the previous Q hacks. Xanadu owns the PennyLane QML platform called PennyLane, and then every year they put on this big event, and a lot of it's virtual, but they were giving away free tickets in person to Toronto on Twitter. So they get all these experts, and it's just kind of like it goes on for several days, and I think it's multiple people a day at some point. But if you want to learn this very well, you have to get exposed to the terminology, and then you have to be researching on your own, and likely giving presentations if you want to make it, and developing your own code, that type of stuff too. But it's kind of like a dense thing that goes on, and I think with a lot of them you can ask questions live just like this too. Okay.
I mean, I really wanted to say thanks for introducing the PennyLane Q hack. I didn't know about it. I checked for the MIT IQ hack, and it starts from tomorrow, and the registration is closed.
Yeah, that's another part. I think that's more in person. I don't know if they do virtual stuff, but I get email regarding
I get you that.
Yeah. Awesome. Any other last questions? So yeah, stay tuned, and I think it's off to, things are very well defined now as far as what quantum inspired means, and where everything's going. Appreciate everybody coming on. This has been discussion 120, Thursday, February 1st, 2024, for basically, a time complexity in QML. Have a good rest of the night, and have a good productive rest of the week. Take care, everybody. Bye.